Welcome back. Now let's look at the third question that we have, right? The third question in the same maze problem is, I want you to find the shortest path, right? So as you know, right, backtracking, we have a goal. In that goal, there is a return true, right? So that's the code where once you have found the goal, we are saying that you don't have to find any other solutions. I have found the solution already and you're returning true. But one maze could have multiple solutions and it could have an alternate path which is smaller than the path that we have found, right? Especially when the maze size is larger, you could have many paths which could lead to the destination, but one would be the shortest path, right? Now, how do you find the shortest path? Assume that all the four directions you can move, right? I want you to again pause for a moment, think what can you change in this code to make sure that it can go and find all the paths, right? Again, for each of these, I'll pause for a moment. I want you to hit the pause button. I want you to think what could be the solution. And then again, if you hit the play button, I will explain what the solution is for this problem, right? So I think in this particular case, the answer is you have to return false. And once you return false, automatically backtracking will think that I have not found the solution in the goal, right? Wherever you have the goal, you have to hit false. So automatically backtracking will think that, hey, I haven't found the solution. It will go and try for alternate paths. It will exhaust all the paths and finally it will return you which is the shortest path. So that is this particular question. Let's move on to the next question. The fourth question in this particular part is the find the shortest corner. That means earlier we said start is at the top left and goal is at the bottom right. Now in this particular question what we are saying is the starting position could be anywhere in the grid. It could be anywhere. Now we are saying that any of these four corners are the goals and whichever is shortest to you, if you reach that, we want to find the shortest path. That means it would have access to all the four ends, right, or four corners. And whichever is the path which is the shortest, we have to return that. So again, hit the pause button now. Think what could be the solution for this problem, and then again when you play you will be able to see the solution, right? In this particular case, again all in the change that is required is in the goal statement. You just have to check all the four corners as the goal instead of just one corner. That will give you the answer for this. So all these are minor tweaks to the code, just adding one or few checks and it automatically gives you the solution, right? So let's look at this code. So the problem that we have in hand is we have to find the shortest path. So we have to allow backtracking to look for multiple options than just sticking with one option. So this is the actual code, right, that we looked at for the last particular maze 2 problem. So now when you look at it, here is the code where it is checking for the goal. So once you have reached the goal, we are saying that you cannot look for alternate solutions. It's sufficient that you have found the answer. So to kind of inform the backtracking that it has not yet found the code, what we'll do is we'll change this to false. So if we make it false, what happens? Backtracking still thinks that it has not yet found the solution. It will look for alternate solutions. Effectively, it is going to look at all the solutions and then finally it is going to say that, hey, I've ran through all the solutions, right? And given that we have mentioned it as false, it is never going to, it's always going to say that no path exists, right? So we are going to make some slight changes here in this code to make sure that it works fine. So first is we need a variable called, so the max or the minimum path, right? So min path or something like that, which we initialize to some big number. So initially min path will be very high, right? And now in this particular case, what we are going to do is whenever it hits here, we are going to check the min path value. Now to find the min path value, I need to know how many steps I have taken so far, correct? Backtracking provides a very easy way to track the number of steps. All you need is you need one more variable called count, or how many steps have you made, right? We'll have a variable called count. Initially, we are not making any steps, so I'm going to make this initial call, the number of count as 0. And whenever you make a recursive call, we are going to increase it by 1, count plus 1. So what happens is when it comes out of the recursive function, right, automatically the count will get reduced, right? So That will automatically happen given that it's a recursion, right? So for that call alone, it will have the value of 1. When it comes to the caller function, it will have the previous value. So if you do this, what happens is for every step that it takes, it is going to increment the count by 1. So now when it comes here, I know that there is a minimum value. If the count value that we have is less than the min value, then we will say the new min is the count, right? So min is going to be the count value. So this way what happens is every time it gets to this point where there is a solution available, it is going to store the minimum count that is available. So this is a very easy way to control the backtracking to say that, hey, you have found the shortest path or not. Otherwise, continue looking for the shortest path. And in main code, the difference that is required is now find solution is always going to return false. We know that, right? Because we are always returning false even if we find the solution. So what we are going to do is we are going to call this find solution, but at the end of it, right, we are going to check if min is less than 1000 or 10,000, whatever be the value, right? If min value has changed, that means you can say system.out.println the minimum steps is, and you can say the min value. This way what happens is if at all the solution is found, it is going to have that value in min. Otherwise you say that there is system.out.println no solution exists. That's it, right? So this way you are actually making the backtracking look for all the solutions, which is typically called the brute force, right? It has gone through all the solutions possible and the minimum value is getting stored in this min value. And when you come out of it after all the recursions, you can print the value. Now if you run this code, so I think I gave it as min path or something. Yeah, I changed this to min path. Okay, let's run it again. Okay, made the changes. So now if you look at it, it's saying the minimum number of steps is 12, right? Let's look at the matrix here. So the input matrix that we had is like this. So let's check if the minimum path is 12, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? So this is the first step. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 steps available for you to get to the destination. That's what it is pointing here to us. So this is the code to find the shortest path, right? Now, along with the shortest path, if I want the shortest solution, right? Currently we have the shortest path available. How do I get to the shortest solution, right? Now, every time, because the solution matrix, if you print now, it does not have the shortest solution, because after all the exhaustive possibilities, the last saved value will not be the shortest path. It will be like it exhausted, right? So it wouldn't have any value. It might even have 0, right? So that way if you print the solution matrix, you will not get anything out of it. I'll also show you the solution matrix, right? We just print the solution matrix just for everyone's benefit. Print solution, right? So if we do the print solution and if I pass the solution matrix, you will see that solution matrix will not have the answer that we are looking for. So it is having all zeros because we said even if you have found the path, go ahead and look for all the combinations, right? So when it finished, it would have something in the solution. It wouldn't have the optimal one. So now what we need is we'll have to save the solution. What we'll do is here, we'll have one more variable called save solution. Okay, or save, whatever you want to do it. So it's called save, right? So and this save also will have the same this one as the actual solution. So I'll have it as save. So this is the save, right? So now whenever we hit this place, right, where you are actually checking the goal and you're getting to the goal, in this place, what we'll do is if count is less than min path, we'll set this min path. Also, we'll save the current solution, right? So for int I is equal to 0, I less than n plus plus I. For int j is equal to 0, j less than n
plus plus j, save of I comma j equal to, we will save it from the solution matrix, right? And what we will at the end of the day print is, we'll print the save matrix instead of the solution matrix, right? So I'll pass here the save matrix instead of solution. So we have the solution matrix, we have the goal check here. Here I have to check for capital. Okay, so let's run this code. Now if you look at it, it is not only giving this one, it is also giving you the path of the solution. So this is the third code that we looked at, right?